Find the x-intercepts in the y-intercept if they exist of the function f of x equals x cubed minus x squared minus 11x plus 11 over x squared plus 4. So we're looking for the x-intercepts and the y-intercepts. I'm going to start with the y-intercept because it's always a little bit easier to work out. When you're finding a y-intercept, you're letting x equal 0, and that means substituting a 0 into the function. Now f of 0 is 0 cubed minus 0 squared minus 11 times 0 plus 11 over 0 squared plus 4. That leaves 11 in the numerator and 4 in the denominator. So we have a y-intercept of 11 over 4. Then we want to find our x-intercept. To find an x-intercept, you let y equal 0. And this is written in function notation, and so f of x is used in place of y. So we're going to let f of x equal 0. That gives us the equation 0 equals x cubed minus x squared plus 11x plus 11 over x squared plus 4. Now this is a rational equation, and we're going to start by getting rid of the denominator, and we do that by multiplying both sides by that denominator. I multiply the right-hand side by x squared plus 4 and the left side by x squared plus 4. On the left side, 0 times anything is 0, so we get 0. And on the right side, we have canceled the denominator, and we're left with the expression that's in the numerator, x cubed minus x squared minus 11x plus 11. Now we want to solve this equation that is left, and we call this a polynomial equation. More specifically, it is a cubic because of the third power. Now to solve this, we are going to use a factoring technique called grouping. And I thought of this method because we have 4 terms, 1, 2, 3, 4 terms. And grouping is a method that typically works with 4 terms. Not every time, but it's a good thing to try when you have 4 terms. So this grouping method says to group 2 terms at a time together and factor the greatest common factor out of each group. So I'm going to group the first 2 terms together, and I'll group the second 2 terms together. And out of each of these groups, I'm going to factor the greatest common factor. The first group has a greatest common factor of x squared. And if I factor that out, I'll be left with x minus 1. In the second group, we have a leading negative term, so I'm going to factor a negative out. And I can also see that 11 is a common factor of each of those terms. So I will factor out a negative 11. If I factor out that negative 11, I have x minus 1 left inside the parentheses. Now at this step is when you'll know if the factor by grouping method will work. Because with factor by grouping, you need to have what's in the parentheses on both groups matching each other. So we do, so this method is working. So I'll factor out x minus 1 from this term, and if I factor out the x minus 1, x squared will be left inside the parentheses. And if I factor out from this term the x minus 1, minus 11 will be left inside the parentheses. Now I can use the zero product property and set each one of these factors equal to 0. X minus 1 equals 0, x squared minus 11 equals 0. And I'll solve this equation that's left. So I add 1 to both sides to get x equals 1. I'll add 11 to both sides to get x squared equals 11. And I can finish solving this by square rooting both sides. And that gives x equals plus and minus square root of 11. So this function has 3 x-intercepts, 1 square root of 11, and negative square root of 11. For this question, we want to find the intercepts of the graph of the function without graphing the function. Our function is f of x equals square root x plus 27 minus square root x minus 3. I want to find the x-intercepts. And to find the x-intercept, you let y equal 0. Now this equation is written in function notation. So this f of x is the y. F of x is the same thing as y, so we're going to substitute a 0 in for the f of x. We have 0 equals the square root of x plus 27 minus the square root of x minus 3. So this is what we call a radical equation, and it's a pretty messy radical equation because it has 2 radicals in it. So the process for solving these types of radical equations is to try to eliminate the radicals. And the way you eliminate the radical is that you isolate it and then do the opposite to get rid of it. So we got to isolate a radical, and the opposite of this, these are square roots, so the opposite of this is to square. But the problem is that you can only do one at a time. So we're going to have to go through this process a couple times to eliminate the radicals, and then once we eliminate the radicals, then you can actually solve the equation. So we're going to start by isolating this radical here. And I first want to add it to both sides. So that'll be isolated on the left. And once you have it isolated, then you're going to square both sides to get rid of it. I'm going to square the left and square the right. On the left, the square and the square root are opposites, and so they cancel each other out, leaving you with x. But on the right, this will get a little bit messy. When we square something, we multiply that base twice. So we're going to multiply square root of x plus 27 minus 3 times square root of x plus 27 minus 3. So we want to multiply this out. We'll multiply the first 2 terms together, then we'll multiply the outside 2 terms, then we'll multiply the inside 2 terms, then we'll multiply the last 2 terms. So we multiply square root of x plus 27 times square root of x plus 27 minus 3 square root of x plus 27 minus 3 square root of x plus 27 and plus 9. Now let's simplify. When we multiply these two together, they both have radicals, and the rule that we follow is that we multiply what's underneath them. So we can write this as square root of x plus 27 times x plus 27. So when you're multiplying the same square roots, you can multiply what's underneath them. Then with these 2 terms, they're considered to be like radicals. You notice that the radical part is the same, and when the radical part's the same, you can treat them like terms by adding their coefficients together. So these coefficients are -3 and -3. We add those together to get -6. and they had the same radical, so we keep it. And then I'll just carry down that plus 9. So then the next thing I want to do to simplify is I've got square root of x plus 27 times x plus 27. That's the same thing as x plus 27 squared underneath that radical. And just like we've seen before, the square root and the square are opposite operations, so they cancel each other out. So this is going to give me x plus 27 minus 6 square root of x plus 27 plus 9. So we've accomplished our first goal, which was to eliminate this radical. But as you can see, we still have a radical in the equation. So now we have to repeat that process over again. We now have to isolate this radical and then square both sides to get rid of it. Before we do that, let's do a little bit of cleaning up. We have some like terms we can combine together. So we have x plus 36 minus 6 square root of x plus 27. And I'm going to start isolating this radical by subtracting x on both sides. And that gives me 0 equals 36 minus 6 square root of x plus 27. I'm going to subtract 36 on both sides. That's negative 36 equals negative 6 square root of x plus 27. And then I'm going to divide by negative 6 on both sides. And I have square root of x plus 27 equals 6. So now I've isolated that radical. And we're going to get rid of it by squaring both sides. Those are opposite operations. So 6 squared is 36. The square root and the square cancel each other out, leaving me with x plus 27. And now I can solve the equation that's left. Now that all the radicals are gone, I see that this is just a linear equation. I want to get x by itself. I subtract 27 on both sides, and x equals 9. With the radical equations, you do have to check your work. Under normal circumstances, checking is sort of an optional step just to be sure that you didn't make any mistakes. But because of this technique that we're using to get rid of the radical of squaring both sides, sometimes this can cause you to have what we call extraneous solutions, extra solutions that don't work in the original equation. So anytime you use squaring both sides as a method for solving, you do have to check your work. So let me zoom out here. We want to go back to our original equation. Our original equation is when we substituted that 0 in. So that was right here. So our original equation is 0 equals square root of x plus 27 minus square root of x minus 3. And I want to check to see if x equals 9 is a solution to this equation. So I'll substitute that in. That's 0 equals square root of 9 plus 27 minus square root of 9 minus 3. 9 plus 27 is 36. Square root of 36 is 6. Square root of 9 is 3. 6 minus 3 minus 3 is 0. So that solution does check out. And 9 is the X-intercept. We could write that as an ordered pair. And this question says, use the graph to determine the domain and range of the function. So when I'm finding domain and range from a graph, I like to use a pencil or a ruler to help guide me. So what I do is, first I'm finding domain, and we're going to write our domain in interval notation. And I'm going to hold my ruler or pencil vertically because my ruler, when it's held vertically, is sort of marking along the x-axis, and the domain are the x values. So I hold it vertically, and I'm going to move the ruler from left to right. Now, the reason why I go from left to right is because when you use interval notation, you always want to go smallest to largest. And on the x-axis, the smaller side is on the left side. So we start on the left, and I'm going to decide when is the first time that my ruler hits the graph. The first time it hits the graph is at -3 at this spot right here. And so my domain is going to start at -3. Now looking at the graph, that point is a filled in dot, which means that -3 will be included as part of the domain. So I'm going to put a bracket on the -3 to indicate that -3 is part of the interval, it's part of the set. So going from left to right, the first time I hit is -3. I continue to hit as I go from left to right, and I'm keeping hitting the graph all the way until I get to this point over here, and this value is 7, 0. So my domain is going to stop at 7 because I no longer hit the graph after that point. And just like on the last one, that endpoint, 7, 0, is a filled-in circle, which means it's part of the graph. And I would put a bracket on that 7 to indicate that 7 is part of the domain. So I've written down the domain now. That's -3 to 7, including the endpoints. So that notation means starting with -3, including -3, and continuing all the way until 7 and including 7. Then we're going to take our ruler and switch it to horizontal to find the range. And now as I go from bottom to top, I'm running along the Y scale now. And from bottom to top, the first time I hit the graph will be at this value here, which is -2, 0, and range are the Y values. So my range will start at -2. That's a filled in dot, so I'll include -2 in the range. And so going from bottom to top, the first time I hit is -2, and the last time I hit the graph will be at this point right here, which is -3, 6, and that Y value is 6. So the range goes till 6. That's a filled in dot, so I'll put a bracket on that. So I found that the domain is -3 to 7, including the endpoints, and the range goes from -2 to 6, including the endpoints. Okay, so I just got pointed out that there's a mistake in my work here, and just want to go back and explain what I did wrong. So when I went from bottom to top, I said the range starts right here because that's where the first time I hit the graph is, and the range are the Y values. So I wrote down the X value of -2 when I should have written down the Y value of 0. So let's correct that. And we have our range starting at 0 and continuing on until we get to this Y value here of 6. So the range is actually from 0 to 6. This question says, use the graph of y equals f of x to answer the question. On what intervals is f increasing, decreasing, or constant? And this is the graph of f, and we see it in red here. And we want to find the intervals for which f is increasing, decreasing, or constant. The words increasing, decreasing, and constant are all referring to the y, what's happening with y, and the intervals are going to be the x. So we're going to describe what's happening to y, but we're describing it on intervals of x. So I'm going to start by just getting an overall understanding of what's happening. I'm going to trace the graph moving from left to right, and I'm moving from left to right to go from smallest to largest. So as I trace this portion of the graph, the y values are constant. We have a y value of 7 along this entire piece, so it's constant. Then the y values are decreasing, then increasing, then decreasing. Then the y values are increasing, decreasing, increasing, and then constant. I'm going to try to label the graph so that I can see all of these pieces separately. So let's start with blue for constant. These sections are constant. We'll go with green for decreasing. So it's decreasing along this section, and this section, and this section. And how about purple for increasing? So this is increasing, increasing, and increasing. So now that I've got an overall feel for what's happening with the graph, I want to write down the intervals. And as I said earlier, the intervals are referring to the x. So if I'm looking at this section of the graph here where it's constant, this x is starting at negative infinity and going all the way up until this x of negative 6. So I'm going to say that this graph is constant, starting at negative infinity and going to negative 6. And depending on your book's definition of increasing, decreasing, and constant, you might put a bracket on this or you might put a parenthesis. For our college algebra book, we use a parenthesis. And then this piece of the graph is also constant, starting at 6, going to infinity. So it's also constant from 6 to infinity. And let's do the decreasing. So on the decreasing section, starting here, it starts at negative 6 and stops at negative 5. We're decreasing on the interval from negative 6 to negative 5, and then again on this section from negative 4 to 0. And then again from 4 to 6. And then we have increasing on the purple sections. That's starting at, I think I need to erase a little bit because I'm getting messy. I can't see my values anymore. So this purple section is starting at negative 5 and goes until negative 4. And this purple section starts at 0 and continues to 4. This one starts at 5 and goes until 6. So those are my intervals of increasing. It's increasing from -5 to 4, union with 0 to 4, union with 5 to 6. This question says, determine the intervals on which the function is increasing, decreasing, and constant. So these words, increasing, decreasing, and constant, these are words that are describing y. So let's get a feeling for the overall sections of the graph by tracing the graph as we go from left to right. So starting at the leftmost part, so the reason why we're going from left to right is because on the number line that's smallest to largest. We want to write our intervals smallest to largest. So as we go from left to right, we can see that the y values are decreasing along this section, increasing along this section, decreasing along this section, and the y values are constant along this section. So I'd like to take a moment and label these different sections. So this section is decreasing, as well as this section here. I'll label that with a D for decreasing. And this section is increasing. I'll label that with I. And this section is constant. Now, when we're asked to determine the intervals on which the function is increasing, decreasing, and constant, we're wanting to write down the intervals of x. We use the x-axis as our kind of map, our way to describe directions on where to look. And so when we write down the intervals, we're going to write down the x intervals for which the graph is either decreasing, increasing, or constant. So I'd like to write down this interval, this first interval that's decreasing, and we want to write down the x where that starts and the x where that ends. So we're going to say that it's decreasing on the interval from, let's see, that looks like -10, and that decreasing interval stops at 0. Now, I'm either going to put parentheses or brackets on these intervals. And depending on the definition that's given to you, in some books you use parentheses based on the definition, in other books you use brackets based on the definition. In our college algebra book, we use parentheses, but in the pre-calculus book I use, they would put brackets on those intervals. So we have another decreasing interval here, and that decreasing interval starts at this x value and ends at this x value. So the next decreasing interval is from 4 to 9. And then we have an increasing interval. And the increasing interval is right here, and we can see that that starts at an x of 0 and ends at an x of 4. Once again, our book uses parentheses on this, but pay attention to your book of whether to use parentheses or brackets. So then we have an interval of constant, and that interval of constant will start at this x value of 9. And because of the arrow, it continues on forever in this direction to infinity. So we found the intervals of decreasing to be from -10 to 0 and 4 to 9. The intervals of increasing are from 0 to 4, and this function is constant from 9 to infinity. Thank you for checking out my videos. Have a great day.